Welcome back, everyone. To finish off our solution lectures, we're going to now evaluate the model that we trained in the previous lecture. Let's get started. Okay, we finished training our model. Optionally, you can go ahead and save your model. The code to do that is just simply saying from tensorflow.keras.models import load_model, and that will allow you to actually load it later. But to save it, you technically don't need to do that import. You can just say model.save and then choose any string code. So my favorite model.h5 and then save that. And if you wanted to load it up again, you simply run load model. So this is totally optional. You don't need to actually save your model here if you don't want to use it again. So let's focus on evaluating the model performance. Recall during training, we passed in both our validation set and our training set. Let's go ahead and plot those out. So we're going to say model history.history, and that returns back this dictionary of the losses, which we can then easily convert to a pandas data frame. And then we'll set that to losses, run that, and let's go ahead and plot these out. So we'll say losses plot. However, if we take a look at losses, right now we have loss and validation loss. So recall, this loss is the training loss. This validation loss is the loss on our test set, that X test and Y test. So hopefully, when we run this, we get to see similar behavior. And it looks like our training loss and validation loss were both decreasing, but eventually we weren't really improving that much on the validation. Something that might be interesting to explore here is to add in an early stopping callback and just train for a lot more epochs and see if this would have continued to decline or if it would have started increasing. Let's go ahead and continue to the next task, which was create predictions from the X test set and display a classification report and confusion matrix for that test set. The way we can do that is from sklearn.metrics. We'll go ahead and import a classification report and a confusion matrix. We can grab our predictions by simply grabbing our model and running predict classes, and then you just need to pass in some features like xtest, and that returns back predictions. In which case, once that's done, we can print out a classification report that takes in, if you take a look at it, whoops, not prints, but the actual classification report, that takes in y true versus y predictions. So we'll pass in y true versus our predictions. And because this is a classification task, recall, we're going to have different, whoops, this should be y test. And as I was saying, because it's a classification task, there's going to be different metrics we can evaluate this by. There's going to be an accuracy metric, a precision metric, recall, and F1 score. So accuracy, that's just the actual percent that we got right. So if you did the same random split we did, the exact same network, we're looking at around 90% accuracy. But recall that in the very beginning of this notebook, so all the way at the top, what we did is we first analyzed the actual label itself, and recall that it's an imbalanced label. So there's a lot more fully paid than there are charged off loans. And in fact, if we were to take a look at a model that simply recalled back any loan as being fully paid, it would actually still be pretty accurate. So we'll scroll down here, and just to kind of show you what I mean by that, if we take a look at our original data frame, and we have whether or not our loan was repaid, what we're going to do is, let's do some value counts here, and we have this many loan repaid. So let's go ahead and take that and divide it by the actual length of that data frame and run that. So notice here that what this is indicating is that 80% of my points were already being predicted as loan repaid, which means if I created a very simple model that simply said any loan will be repaid, I would be 80% accurate. So don't be fooled by a model that returns back 80% accuracy, because by default, a model that just always reports back that the loan will be repaid itself will be 80% accurate, more or less, on this actual test data set. So we should be looking at kind of a bottom threshold of 80%, which means our 89% accuracy here is okay, but it's not absolutely fantastic because of our imbalanced data set. As mentioned in the machine learning metric lectures, the actual metrics we want to take a look at are precision, recall, and F1 score. And it looks like, depending on the class, we perform a little worse. So the true class we should be looking at here is the one that's lower representation, which is 0. So note we have a lot less instances of 0. We're pretty good on the precision here, but really where we suffer is the recall. And we can get an F1 score, which recalls the harmonic mean between precision and recall. So really, the true notification of whether or not this model is doing well is this F1 score on this 0 class. So what I would encourage you to do is see if you can play around with the model hyperparameters, maybe add in more layers, add in more neurons, maybe play around with the dropout rate to see if you can improve off a base 0.61 F1 score. Okay, so is this good or bad? Well, that really depends on the entire context of the situation, whether we have a model that already attempts to predict this and what's its F1 score. So we need a lot more context to decide whether or not this recall and this F1 score are good enough. What we can say right off the bat is that this accuracy is better than just kind of a default guess, which would be 80%. So this model is definitely better than just kind of a random guess or a straight guess. So we are performing much better. A random guess would get 50% accuracy. A straight guess of always being repaid would get 80% accuracy, and our model is getting 89% accuracy. So we are performing better than both a random guess and a straight loan repaid return. Okay, so overall, we can see that our model is learning something from this data set. And then we can see the confusion matrix as well. If we're interested in that, we can perform y-test versus predictions, run that, and we get to see this confusion matrix. And again, you can see we're misclassifying a lot of those 0 points, which causes this kind of low recall. Okay, so given the last task of giving the customer below, would you offer this person a loan? What we're going to do here is basically use our model to run on a single person. So we'll simply import random seed, set it to 101, and then we'll create a random index using this. Then off this random index, we're going to grab some new customer and then display their actual features. So go ahead and run this, and if you ran everything the same, you should get the same random customer that we got, and you can play around with the seed if you want a different random customer. And the way we would actually predict off this customer is first we have to make sure that this is no longer a Panda series, but actually a NumPy array. So this is kind of the hardest part, is making sure your data is in the right shape. So a new customer right now, it's a Panda series. What I need to do is grab the values, which returns back these feature values. And then after that, I need to reshape this to be in the same shape of the training data that the model was trained on, which in our case is 1/78. And that essentially adds a little extra bracket call there, which is what our model expects. And then we're going to go ahead and make sure that we scale this data in order to predict the correct class. Because recall, our model learned on scaled data. So we will take our scaler and we will transform this data and set that to our new customer. So we'll say new customer, run that. Let's go ahead and check out our new customer. So now we have a scaled version of this new customer, and let's pass this into the model. Say model predict classes on this new customer, run that, and our model predicts that it was a 1. So now let's actually check, did this person actually end up paying back their loan? So what we're going to do here is essentially run this same command here, but we won't actually drop it. We just want that actual column there, run it, and if we look at the very bottom, or we can just call it ourselves, we want to see whether or not the loan was repaid, and it happened to be repaid. So it looks like in this particular case, we got it right. All right, so that's it for this project. Notice it was a very large project, but a big part of it was actually feature engineering and understanding the data. Usually when it comes to actually training the model itself, that's a much simpler task because the model is doing most of the work. All you need to decide on is how many layers and how many neurons per layer. So there's lots of options to play around with here, and I would encourage you to play around with your own models and see if you can beat our performance that we've shown here with this simpler model. Thanks, and I'll see you at the next lecture.